Well, hello everybody. So this week we're going to jump further into our review. We're going to review kind of the back half of topic 4, and I'm going to go over some key skills that I think are super important, but I think we might have missed the mark a little bit on them. So I'm going to take this as an opportunity to come back, we'll brush up on it. And so we'll kind of do a quick brush up on expanding. I'm not so worried about that. However, knowing how to expand is going to be a good leverage point how to jump into factory. So I'm going to quickly go over expanding. We'll jump into how to leverage that to factor because we're going to kind of unexpand with that. And then we'll jump into something that was a little tricky for a lot of students, subtracting expressions. So I'll put little timestamps on the YouTube video. So if you're like, oh, I'm pretty good with expanding, I want to jump into factoring, I'm pretty good with factoring, I want to jump to subtracting expressions, you can just click the buttons on the bottom of this video. It'll be below the video itself in sort of the little description section. But I'll enable that. Let's go ahead and jump in. So first, let's take a look at expanding. And I'm going to show you two different ways to expand because I think it kind of helps leverage that into factoring. So we're going to take an expression and I'm going to throw in some negatives at you as well, so know how to deal with that too. So let's take something like -6 times 3x plus 2. So we're going to start with the box method. So remember, whenever you have a number next to parentheses like this, you have an implied multiplication. So this is like -6 times 3x plus 2. So we're going to start, we'll just model this as a box. So I'm going to draw a little box. I'm also going to draw a little line through it. Because if we have multiplication, that's essentially like -6 right here being multiplied by 3x plus 2, where this whole section, or this whole side length, if you got a section that's a length of 2, a section that's a length of 3x, that is like this portion of the box, or the horizontal dimensions. And then you can just model it as if this is the vertical dimension. And then we just go through and multiply. So I'm going to go through to make this a little simpler. I'm going to take away our parentheses because we don't need them anymore. We know we're multiplying both. So I'll start. Now you just multiply. So -6 times 3x. Let's remember our multiplication rules. We got a negative times a positive. So that must equal a negative. So we've got a negative 6 times 3, 6, 12, 18. That would be 18. And don't forget, this is a 3 times x. So this is like -6 times 3, which is -18, times an x, which you can just write that as -18x. All right, next, we do the same thing here. So if this is -6, this dimension over here is -6. So to get the area of this box, we do -6 times 2, negative times a positive, unlike signs, it's got to be negative. 6 times 2 is 12. And we have that this expression is -18x plus -12. So the statement I can make from that is -6 times 3x plus 2. Well, that is the exact same thing. It is equivalent to -18x minus 12. We've expanded this. We've dealt with the parentheses. They're done with. Now it's just a linear expression in standard form. Much easier to work with. In most cases. Sometimes you would want this, as we'll see later. So now we're going to go to the arrow method. We've got the box method down. And this is kind of to say we do not need to draw the box the whole time. We could model it as an area, side length times side length. However, we can do that same operation by doing something called the arrow method. So I'm going to copy that expression down. We got -6 times 3x plus 2. And you'll notice in this example where we modeled it as area, we had -6 times the first term. To get this inner box, or this leftmost box, we did -6 times 2, the second term, and we just got the rightmost box. So I'm just going to do that without drawing a box now. So why we call this the arrow method is what I'm going to do is I'm going to take the term that's on the outside, this -6 here, and I'm going to draw an arrow to the 3x, and I'm going to draw an arrow to the 2. And what I'm notating here is that's just this distributing through as multiplication. So essentially what this becomes is -6 will deal with the first arrow, -6 Let's erase that dot really quick. Negative 6 times 3x, and then we'll just add on negative 6 times 2. This times this, here's the second arrow. And so, we don't want a little dot there, so let's fix that real quick so no one gets confused. Let's erase that. There we go. And now we just simplify it out. So negative 6 times 3x. We can do this shorthand way, or we can do this a quick way. Negative 6 times 3, negative 18 times x. And then here, plus a negative. If we get here a negative 12, we can write this as plus a negative 12. But of course, we know from our addition rules, that's just the same thing as minus positive 12. So we'll simplify it like that, whether we use the box method or the arrow method. You can see we get the same thing. So if you want to lean on the box method, go for it. If you feel like you've kind of mastered, you know the conceptual, go ahead and use the arrow method, but it's good to know both. So next one we're going to look at is how do I factor? How do I undistribute? So essentially, I'm just going to make up something that we can factor. So let's take just a linear expression. We'll do 4x plus 12. Essentially, what we're going to try to do if we factor is we're going to try to turn it back into something like this, where it's a multiplier on the outside. You've pulled something outside, and it's just one number times a linear expression. So term times term, we're going to try to factor it, try to undo the process of distributing or expanding. So what I'm going to do here is I'm going to try to find the greatest common factor. So eventually, just give you a preview of where this is going. We're going to try to work this process of a box backwards. And I'm actually just going to skip forward to see what we're going to do here, and we'll kind of revisit that. But essentially, if I'm working this process backwards, well, at the end, I got what's inside the box. Now I'm going from what's inside the box to what would be outside the box. So what I'm going to do is I'm going to take both of these terms, I'm going to put them inside the box. So I'll put the 4x here, put the 12 over here. It doesn't matter if you reverse these. It's just addition. So this is like a 4x section plus a 12 section. And eventually we're going to work to what's outside, but we're going to do that in a step-by-step process. So I'm going to start, if we're factoring, I better find the greatest common factor. So what I mean with greatest common factor, you think of factor, something that multiplies in cleanly, like 4, you could multiply a 1 in, 2 goes into 4, 4 goes into 4. Now we're trying to find the greatest number that is common to both. So what I'm going to do is I'm going to take the 4x and I'm going to take the 12 and I'm going to search for factors. So I've got factors for 4x, like I could multiply 1 by 4x to get 4x. I could multiply 1 by 2. I could multiply 2 by 2x to get 4x. I could multiply 4 by 1x. And I could also do x, 2x, and 4x. But there's no x's in here, so we won't really worry about these for now. 1, 2, and 4 are the numbers that will go in that we're going to worry about. So now we'll list out the factors of 12. So 1 goes into 12. 2, I can multiply 2 by 6 to get to 12, so that works. 3 times 4 is 12, so I know 3 and 4 are both factors. Of course, 6 times 2, so let's list the 6 out. And of course, 12 times 1 is 12. That's another factor. So we've listed out all the factors of both. I'm just going to go through and find the greatest common. So 1, it's common. It's not the greatest, though. 2, it's common. Not the greatest, though. Here's what we arrive on. We've got the 4. So, of course, I could put like a 2 or a 1 out here, but it's not fully factored. So we're going to choose our greatest common factor, and that greatest common factor is going to be out here. The reason I chose that is because I know I have to multiply this number by something to get to 4x and 12. And because I use this process to find the greatest number that multiplied into both, I know that's the number that goes out here because it's going to eventually multiply into both. And so now I've essentially solved one piece of this. I know what goes out here. I don't know yet what goes in here though. So I've partially factored this. I haven't done it completely yet. So now the game becomes, well, what goes up here to find this piece, and what goes up here to find this piece. So I'm going to search using my knowledge of multiplication to do this. So if I have 4 times a number is equal to 4x, it just becomes a puzzle to figure out what that is. So 4 times x is 4x. So I'll just put an x up here. And now I actually have to figure out 4 times what is 12. And now I just game that out. So I could do 12 divided by 4, or if I just know kind of that property, I know that 4 times 3. And we could check this out. 4 times x, 4x. We've checked our work there. 4 times 3, that's 12. Checked our work there. So a lot of students will stop here, but you've done all this work and you actually haven't made the final product. So what we're going to do now is put it into this factored form. So what I'm going to say here is I had my original expression, 4x plus 12. And through this area model here, what I have proved is the exact same thing as its factored form, 4 times x plus 3. And we have factored this expression completely. Yay! All right, one more example I want to show you, one that I think students found a little bit tricky, is subtracting expressions. So we're going to take a look at subtracting expressions really quick. Another way to state this is, what do you do if there's a subtraction symbol being applied to a parentheses? So this one's kind of tricky, but hopefully this will kind of revisit this, make a little bit more sense. So what I'm going to do is I'm going to draw 2 boxes. Maybe I'll make one of them a different color. I don't want the inside there. Let me redo that really quick. So let's go there. Let's do, oh, still didn't do it. Yeah, that'll be fine. So what I'm going to do is I'm going to couch this in area, because I think when people see area, they understand what's going on a lot more, rather than some kind of nebulous concept of like footballs or like the weight of something. Here we're just dealing with area. You take something away. So what I'm going to look at is I'm going to look at what happens if I take this and I say, let's just use the expression we had earlier with 4x plus 12, and I'd say that's the area of box number 1. And I say we've got an expression for, and let's even specify that it's area. And we've got an expression for the area of box number 2. And I'm going to give this an actual area as well, and say it's got 2 components. Let's say the left half of the box has an area of 3x, and the right-hand side of the box has an area of 10. So what I'm going to do now is I'm going to say, what if I wanted to find the difference in area? How much bigger is box 1 than box number 2? Another way to say that is we're just subtracting here. So I'm going to put a big old subtraction sign in the middle. So if I looked at this, I could say, well, why don't we group the things that are like terms? I could take 3x away from 4x. So I could say, well, I've got my 4x box. I got to take away my 3x box. And of course, I think we can game this out in our heads. That's just going to be a box worth of x. But I've only dealt with this box and this box, or this portion and this portion. So let's also deal with, we could take the 12 and say, well, this is added to it, so I better take it away from the 12. So let's take the 12, take away the 10, and I get the difference, or how much greater this section is 2. So I could say the difference between these two is equal to the expression x plus 2, and I can keep it drawn like that. So now let's look at what happens, because this is where the error comes into play. What if I did this only using expressions? So I'm going to make a mistake here and show you why this is so important. So I'm going to make a purposeful mistake. So what I'm going to do is I'm going to write the expression 4x plus 12. Now we want to take away 3x plus 10. So I'm going to take away 3x plus 10. So if we do our like terms combination, well, 4x minus 3x, that gives us x. Well, we're good so far. That's what I wanted. I wanted x. And now I do plus 12 plus 10. And that is 22. But the difference wasn't x plus 22. It was x plus 2. So what went wrong? So if we go back and I look at this, and I looked at this conceptually, if I'm thinking about this conceptually, it should be very obvious that I can't take this portion of the box and add it to this portion of the box if I'm trying to take this portion away. So what I should have done here is I should have put parentheses around here, because it's really this entire box, and we could even add a parentheses here and just drop them later, minus this entire box. So I'm going to put some parentheses just like I did in the expression down here. And then what you can see is, if I'm to do this correctly, so the first set of parentheses, it doesn't matter. You can think of this is just a positive quantity out here. We have a positive area here. We can just drop the parentheses. However, if I look here, I'm really subtracting off the 3x, minus 3x, and I'm subtracting off the positive 10. And now you can see I get the 2 here. Another way to think about this, and I'm going to work it backwards real quick. If you ever see a negative being applied to a parentheses, and what do I mean when I say applied to a parentheses? I mean that it's on the left-hand side of the parentheses, meaning it's saying subtract off this stuff right here. And so if I have that, what I can picture here, and I'm going to erase this ever so slightly to give you some room, but what I can picture here is this subtraction. It's like saying I'm subtracting off one of these. And then, if you remember all the way back to that first example we did, I just distribute that -1 just like I would expand. So here, we get the same thing. It's like taking a -1, and if you want to, you can think of this as like a plus -1 of these, because subtracting one of these is the same thing as adding a -1 of them. I distribute the -1. So here on the right-hand side of this expression, -1 times 3x, that's -3x. -1 times 10, that's -10. Here, this first part, there's just an addition sign in front of it. We can just drop the parentheses. 4x plus 12. And now you can see when I group these like terms, I'm going to get the correct solution. I'm not going to get some weird like 22 out there that makes absolutely no sense. So take the 4x and the 3x, combine those. I get 1x, of course, which I could write as just x. And 12, group it with the -10, or subtract then. 12 minus 10, that gives me plus 2. 1x plus 2, which is the same thing as x plus 2, which is exactly what I wanted. So hopefully this is helpful. I'll post some practice on these. Next week we are jumping into new content, so be ready. So I will see you guys in the Wednesday meeting. Take care.